We need to close the button. Okay, so if you have any, tomorrow we have a what to say how to say presentation. Still have 3 person, right? Zeri and Sling and Xiaotong. So tomorrow 2 o'clock. See you at A511. What did I say? 119. A5119. Okay, 2 o'clock. So 3 of you, I think we can finish within half an hour. A5119. Okay, A5119. Time at 2 o'clock. We can finish within half an hour. Should be. Okay. Right. So where have we been? So we have been in the second last chapter, which is infinite series. So infinite series is already covered in calculus 2. Okay. So what we did now is just fill in the rigorous gap. Okay. So we will prove why you can use, for example, ratio test, group test, divergence test, simple comparison test, limit comparison test, alternating series test, right, and so on. Okay, so we will prove all these. We will quickly go through. But what I want you to appreciate from this proof is how we combine the knowledge of epsilon, delta, okay, and limit. Okay, how we combine these ideas together. So you can see that in the first half of the course, we investigate what is limit, what is sequence of a number. Okay, we study the limit, we study the upper bound, lower bound. Okay, and then in the second half of the course, we use this to define integral. Okay, convergence of series, for example. Okay. All right. So the last step, last place we stop is about this theorem here. So if we have a series, okay, when is this series absolutely convergent? Okay, so why we want to ask about absolutely convergence? Is the thing we say. Why do we care about absolute convergence? What happens if a series absolutely converge? What does the absolute convergence test say? If a series absolutely converges, then no. That one is definition. What's the implication? Can we say something about the original series or not? If a series absolutely converges, then the series converges. Okay, so absolutely convergent is stronger. Okay, that's why we say absolute. Okay, absolute function. Okay, if a series absolutely converges, then the series converge. So we can say what happened to the original series. Okay, by proving a series absolutely converges. So there's a criteria, sufficient criteria for a series to absolutely converge. So what's the criteria here? If you can bound the subsequent terms using the previous term by some constant. Okay, by some constant. What's this constant here? Where does R live? Easy. Where does this R live? Where does R live? 0 to 1. Okay, cannot be too large. If you put 2, 3, 4, there's nothing to control there, right? It's very big. But what happens for R in between 0 and 1? You make the number smaller, correct or not? half, you half the value, or 0.6, 0.7. So you take smaller value. If this R is like 2, 3, 4, 5, 6, 7, 8, it's so large, nothing to control about it. So we want this R to be small. Okay, we want this R to be small. Okay, so yesterday we proved this using geometric sum series and monotone convergence series. Okay. Right. So today we're gonna use this statement here to prove a corollary, which is the ratio test. We will use this statement to prove ratio test. Hey, did ever go to a classroom that have a lot of whiteboard, blackboard, they can slide through one? Where
A2 10301.
Oh, A2 got I see. Okay. So I mean, previously our classroom is like that when I was in the university. So when the lecturer writes, right, finish a blackboard, he just pull that blackboard up. So they won't erase the thing they wrote. Okay, so you can refer. But now we have some short text here. I have to go to the next page to write, right? So if you want to keep this page, I recommend you can take a photo first, because sometimes I will refer back the lemma, okay, or refer back the definition. So if you cannot remember the lemma, cannot remember the definition, you can take photo first. Okay, then I can go down to a new page. Does it make sense? Okay, no? Yeah. Unless in future we have a multiple projector, maybe, so we can make different screen. Okay. Yeah. For now, you can take photo if you forget the statement. Okay. So what's the corollary here? So let's bring this corollary. So we will prove this statement here. Okay, so we'll prove this. So there are three statements for this ratio test. If the ratio, absolute value of the ratio, the limit is less than 1, then it converges. Absolutely. If greater than 1, diverges. Equal to 1, don't know. Okay. So we'll focus on proving the first one first. Okay. Do you reckon that we can use the lemma before? No? Okay, what does the lemma require before? What's the sufficient condition then? An plus 1 has to be less than equals to r times an. Okay. But here, do we have this condition or not? Do we have this condition here? Is it true here or not? If we have a previous condition, okay, that means that, so let's do some working here. Let's do some working first. So if we have this inequalities here hold true, this one is true for all n, then what is true is the absolute value of an plus 1 over an is also less than equal to r. Correct or not? Okay. But then this will imply what? If I take limit for n to infinity, what can I say about this limit here? If everything is already less than equals to r, then what's the limit? Everything already less than equal to r. So what's the limit? What could the limit be? Also less than equals to r. We cannot say much. Okay? 对不对？全部小于等于1的东西，它可以最远去到哪里？不可能超过1的吗？它只有可能是小于等于1吧。OK， 说我不能够讲什么，因为我不是很懂，对不对？我只知道它小于等于r吧。但是 but what this question say is exactly equal to L. exactly equals to L. So do you reckon that this equals to L, we can use inequality like this? Okay, how do we apply it? Okay, how do we use the limit definition to get this first inequality here? Okay, so how do we get it? So what's the difference? What's the difference between limit and this kind of inequality? What do you think about? How do you think about this limit here? How can a number, a sequence of number limit to a value? How do you approach a limit? Do you remember the general picture or not? Do you remember the general picture here? So, okay. So if I write like this, okay, what's the general picture you should think about it? What's the general picture you can think about it? Sequence of number, right? So you can think of it as a function from n to r. And let's say this line is L. How do you approach L? How can you approach L? How many ways you can approach L? 3 ways. What are the 3 ways? You can go down like this, right? You also can go up like that. And then maybe you oscillate in between. Correct, that's right. This is the general way you can approach them. Or you can take combination of them, right? For example, you decrease downward and then up a bit. And then do this also can. Right, okay. So the difference between this limit and this inequality here is this inequality here make sure that you can approach the limit from the bottom. Okay, from the bottom. Okay or not? Does it make sense? Okay. So what we're gonna do here? Okay, so what are we gonna do here? So how do we prove this? So we are trying to play a trick. Okay, let me show you the trick and then we'll see why this trick works. So first, suppose that L is less than 1. Okay. We won't show that Ln plus 1 is less than or equal to L times An, but we will take another R. Instead, we will let R equals to 1 plus L over 2. Okay. What is this 1 plus L over 2 doing in this picture here? So if you look at this 1 plus L 1 plus L line here, okay, where is over 2? Over 2 is in the middle. Correct or not? Okay. So what am I doing here actually in this picture here? I know that my series will get very close to this L line here. So what I do is I put this line a bit higher so that I can consider all the terms in my sequence. Does it make sense? Okay. Let me show you what happens. I pick this L here. What we can say about this L? Sorry, this R. So since L is less than 1, okay, R is also less than 1. Okay. Since R is less than 1, since L is less than 1, R is also less than 1. Okay. But this R is good. Why is it good? Because we can choose n in n such that for every n greater than n, an plus 1 over an, which is equals to an plus 1 over an absolute, which is what? Which is less than R. Does this work? Is this the definition of limit or not? Does this work? Huh? Does this work? Where's the epsilon here? What's the epsilon I'm using here? And what's the epsilon I'm using here? Okay, so maybe we go back a bit. So let me put another working here. So let's put a working box here. Working. So limit of n to infinity of an plus 1 over an equals to L means what? For every epsilon greater than 0, there exists an n such that for all n greater than n, the absolute value of an plus 1 over an minus L is less than epsilon. Okay, but what's the R here? What is R? How we pick the R? R is what? Sorry? Say again. Is equals to 1 equals to 1 plus L over 2. But how do you realize as this epsilon thing? Huh? How do you realize an epsilon thing? So what's the epsilon we pick here if I write like this? So if you want to see the epsilon, you should take minus L on all sides, right? Okay. But what's left here if you take minus L here? What is this? R minus L is what? 1 minus L over 2. So this is the epsilon we take. 1 minus L over 2. Is it greater than 0 or not? 1 minus L over 2. Is it greater than 0? Epsilon have to be greater than 0, right? Is this 1 minus L over 2 greater than 0 or not? L less than 1, right? So 1 minus something less than 1 still positive. Positive divided by 2 still positive. Okay? So this is the epsilon I pick here. Okay? To make sure that our term here, an plus 1 over n is less than r. So this is how we use this definition here. Does it make sense? Okay or not? No question? Question? Please, I must ask question. Otherwise, I'm talking myself. Any question? No? Can follow? We are trying to use how to say 活用那个 definition of limit 我们不是死的一直要去找 epsilon 还是什么 OK 但是你要我找我也找得出那个 epsilon 你要的这个意思明白吗 OK OK no question OK right so what we have got here is we got that so what we got here is the inequality here less than r for all n greater or equal to n. Okay, so meaning what? If you look at the picture here, we cannot get this, although we cannot get the inequality here for the terms before n, but after n, we can make sure that this inequality holds here. Okay, the inequality holds here. So this says what? This proves that the infinite series of k from n, k from capital N to infinity of ak is absolutely convergence. Convergence by previous lemma. Okay, by the lemma we talked about just now. But you see, this implies what? If I know this sequence is this series is absolutely convergent, this implies what? This series is also what? Converge. Okay, good. So this series also converge. Hey, by the way, our question here is asking from k equals to 1. I only prove from k greater than n converge. Does this imply the k equals to 1 series converge or not? Why? 1 to n is just finitely many number. So this will implies that the sum from 1 to infinity also converge. Okay, make sense? Okay, good. Okay, so the problem here, if we only have the limit condition, we only can prove that for certain n, after certain n, it converge. But that's good enough already, because the first finitely many sum is finite. You can add that finite sum to the converge term. Okay, then still a finite sum. Yeah. Does it make sense? Okay or not? So this is why we have this ratio test. This is why we have the ratio test. So similarly, so I think we won't prove the divergent case. So we will leave divergent case for exercise. Okay, we'll leave the divergent case for exercise. I'll prove the proof inside my note. Okay. So any question about this proof or not? About the proof of ratio test when it converge? Any question? Yes. That's right. So when we pick this R, we already assign our epsilon to be 1 minus L over 2. That's right. Arbitrary means what? If it converges, then you can use any epsilon you like. No? Right, no? No need, no need. What does this arbitrary means? What does this arbitrary means? Meaning if you put any epsilon, I can give you an n. What we want is we want to find the n. So give it the epsilon I need. No? That works for me. What works for me is this R here. So for this R to work, I need to pick an epsilon that is allowed for the limit. Does it make sense? So I mean here your point is how to apply definition. Okay, we want to apply definition, not prove the limit exists. Prove and apply is different, you know. So let's say we have this definition here. If I want to prove means what? I need to check for all epsilon. But if I want to use it, if I want to use it, how? Any epsilon greater than 0, then I can use this sentence. So now we are just using it because we already know the limit of an over an plus 1 over an is equal to L. We already know. We don't need to prove anymore. Okay. What we want to get is this bottom inequality here. Okay. What we want is this bottom inequality here. This ratio is less than some number less than 1. This is what we want. And how we get this R from this proof is not by L itself. Okay, a bit greater than L. A bit further than L. Does it make sense? Okay, if you think about it, why I need something a bit greater than L? Exactly, we have this kind of cases that if you pick L, some terms maybe acid L, some term, okay, maybe acid L, right? 超过 L 对不对？这样就不好了，因为我要从下面上去，对不对？还记得吗？这个 lemma 告诉你我要从下面上去，我要从下面上去怎么办呢？L 不能哦，那我拿 L 高一点点哦，对吗？我拿比 L 高一点点的数字哦。为什么这个可以 work？ 因为这个是 limit 的概念，这是 limit 的概念。 看到 limit 的概念，这个是什么？我把它拆出来。Okay, we can further decompose this. This would say that an plus 1 over an is less than L plus epsilon and greater than L minus epsilon. So 这里你看到什么东西？有看到东西吗？这里的东西告诉你什么？所有的 term 是小于 L 加一个 positive 的 epsilon。我只要比这个 limit 高一点点，全部人都在我下面的。For some n, okay, for there exists some n such that for all the little n after greater than n, it lies below L plus epsilon. Does it make sense? 可以想到吗？可以 imagine 到吗？可以 imagine 到吗？啊？可以 imagine? So for every epsilon greater than 0, there exists n greater than n such that an plus 1 over an absolute value is less than L plus epsilon greater than L minus epsilon. Okay? So 我要的是这一个 part， 因为我要从下面上去这个小于 r 的小于1的 r， 对不对？明白吗？但是你又不可以加太大这个 epsilon 哦，你加到你的 r 是大于1，你就不能够用前面的 lemma 了，对不对？但是你要加足够小的 epsilon， 但是足够小的 epsilon 这个 limit 就是可以让你做这件事情啊 ，for all epsilon 啊，足够小 ，OK 了 ？Does it make sense? Does it make sense? Okay, so this line here, what did we wrote here? This line is L plus, what is the epsilon we use? 1 minus L over 2. Okay, this is the epsilon we use. Okay, so how do we denote this epsilon? Epsilon is here, this distance here. Does it make sense? Okay or not? Question? Other question? So this is the idea how we use limit. Okay, how we use limit. Any other question? Any question? One last question maybe before we continue. No? So far? Okay or not? This is the thing you want to train yourself to think about this concept. It's not about a calculation, but this concept is very important. How you apply the definitions. Okay, how you use the definition. Why? How you appreciate the definition. Okay, how useful is this for epsilon, for all epsilon? Okay or not? Okay. All right. Next, we'll continue. To leave out the proof for divergence is quite similar. It's quite similar, but you need to show for unbounded. So next is root test. Okay, we will do root test as well. So what's the root test here? Maybe let's get it here. Root test. Okay. So what is root test here? So root test meaning you need to take root of your terms in your series. So what's the root you take? You take n root of the absolute value of an as well. So where's the limit here? So when you take further an, you pair it with higher power of n root. Okay. So a1 pair with no root. A1 pair with no root. What is root 1? Okay. A2 pair with root 2. A3 pair with cube root. A4 pair with quadruple root. Okay. And then 5th root, 6th root, 7th root, 8th root, 9th root. Okay. So on. So if you found that the limit of this number is less than 1. Okay. It's less than 1. Then, like ratio test, the series also converge? Absolutely. If it is greater than 1 or equal to 0, it also diverges like a ratio test. If it is equal to 1, it is inconclusive. So you can see that the condition here is slightly similar to what we have in ratio test. But surprisingly, this proof is much easier than ratio test. Much easier. Okay, let's see why is it much easier here. So we say similarly, we're gonna play around with the property of limit here. Okay, we'll play around with the property of limit here. So let's prove the first case. Okay, prove first case. So suppose L is less than 1. Okay, so if L is less than 1, how can you apply this limit here? Okay, then there exists an R with L less than R less than 1 such that there exists an N in N if for all the terms behind this N, square root of N modulus AN is less than R. Okay, can everyone follow this one? Why is it less than this R here? What's the epsilon I use here? What's the epsilon I use here? What's the epsilon I use here? R minus L. Okay, so this is the epsilon I use here. Make sense? Okay, no? Okay, so this is the epsilon I use here. Correct or not? Limit, remind yourself what is limit. When I talk about limit, you have to be like a, how to say, computer, ChatGPT. What ChatGPT tells you, it will tell you for every epsilon greater than 0, there exists an N in N such that for all N greater than N, then what? Then the absolute value of this terms minus L is less than epsilon. But what is this? This is just square root N of AN minus L is less than epsilon and greater than minus L. So what we are interested is the part at the back. Okay, we are interested in the second inequality here. Does it make sense? Okay. Okay, so we are interested in the second inequality. All right. To this end here, what do we get? We have this inequality here. What can we play around with this inequality? Do you reckon? What do you reckon? Yeah, you can take to the power of n to on both sides. On both sides. Of course, this requires proof. Okay, this is the something we should did in the first few weeks. Why you can take n roots on both sides. But it is not too hard. Not too hard. You just apply the b less than c and then a less than d and then y a b greater than c d, something like that. Okay, apply multiple times. Okay. All right. So to this end here, okay, to this end here, can you comment why the sum of an have to converge? What is R? Quantity less than 1. Greater than 0. Is it greater than 0? Just less than 1. Okay. And then it should be greater than 0, right? Because the terms we're looking at is all absolute value of an, so must be non-negative. Okay. So L have to be greater than 0 and less than 1. So what's this? The series of this guy? Series of this. It's a geometry series, right? So by simple comparison test, okay, maybe before that, maybe add one more line, maybe you are more familiar. So you can write like this, right? Okay. Since every sum is less than, every term in the series is less than each other, then not each other, one is less than the other, then the series of an is less than the series of rn, r to the n. So by simple comparison test, the series of absolute value of an converges. Okay, why? Because the geometric series converge. Okay, no, still remember, no? Geometric series converge. Still remember? What's the sum to infinity for this geometric series? 1 over 1 minus r, correct. Okay, so this is where it converge. Where it converge to. So because this guy converges. Okay, so since the sum of an absolutely converges, absolutely converges, the original sums must be convergent. Okay, the original series converge. Okay, no? Okay. Actually, the proof for divergence even easier. Proof for divergence is even easier. Can you try and think about for 2 minutes how to prove for divergence? Suppose L is greater than 0. Proof for divergence is even easier. Can you try and think of a minute? Why is it true? It's even easier. It's even easier. I think a minute. Why is it true? It's even easier. You only need to use a definition of limit and also a definition of and also divergent test lines. Two lines. Okay, anyone got idea now? Limit of all these terms equal to L means what? There exists an n such that for n greater than n, all these terms should be greater or equal to 1. In other words, what this means? Absolute value of an is greater or equal to 1. Then what this means? Then an cannot have limit 0 because it's at least 1 away from the 0. Okay, all the term is 1 away from 0. Either greater than 1, either less than or equal to minus 1. So by divergent test for divergence, the original sum should diverge. Yeah, proof for divergence is even easier. Does it make sense? Okay, now. Any question? Or question now? Okay, we are slightly advanced in using limit now. We are like no need to specify too much about epsilon. We know what we want to take for epsilon. Okay. Yeah. Any line doesn't make sense here? Question before we break? No? No? Please ask question. Don't be shy. Please ask. Because your question maybe is also others' question. Okay. If no one asks, then no one knows. Yeah. Yeah. Okay, if no question, maybe we take a break until 1:04. Okay, we'll take a break until 1:04, and then I bring some snack here if you want to pass. Become a canteen. By the way, this snack is my childhood snack. Yeah, it's very nice. Childhood snack. I can take more than one if you want, provided everyone already taken.听见了？也
我这样子东西，开始用这个了。
这样。
因为我才说上面给我有没有然后一问他有看不懂，他也还有什么？
对。
我是只要写这里还是我还会就是不懂。
比较重要是这个东西吧。
这个
比如说你要讲它 conversion，然后为什么可以用那个你的快来讲？
是我
然后的话就大概讲我这个东西用在什么，讲我用在什么情况，也。至于这个讲用在这边啊，就这样，
就是这样，我的
讲用在对。
然后那时候就说，
嗯。
我证明到这个东西，这个东西要讲这个的，什么？
这个
今年那时候
没有这个是为了解决这一个东西，这个就是头跟尾巴，对不对？这一行在解决这个三吧。三你知道是什么吗？不，这个是小于等于它不等于这两个等于哦。
哦，所以那个这个展开，
诶，
这个
没有这两个等于我想讲。
对呀，就是这个
对
这整个东西，
对，
这个的也是
等于啊，
等于
对，没有这一行等于这个小于这个。
那我要讲用这个
不是，它的原因是这个，它这个是讲像之前的情况，所以原因在这里啊。这一个你知道什么原因吗？
这个我操你，
这个 monotonic 是说这个 an 可能是下来的，或者一直往上的，对不对？所以如果假设一个情况呢，一直往上，往上有一个情况，比如说1、2、3，所以这里取的是什么？二跟一的距离，三跟二的距离。但是这两个的距离加起来是不是就是等于三跟一的距离？平时不对的，你知道吗？是因为它这样子增加我才可以
一直这样，
啊，一直你的 distance 是啊，你一直这样贴就不可以了啊，对不对？但是它是一直贴上，就是才会等于，所以它这里的意思是 the monotonicity of an implied 嘛。等一下我们要上这个，不然你来帮我上。 你看，感受好是天法官啊！我。
哦，你要看我这边随便啊。
节目时间到，对，就对了。
我要带上来喝，我太想睡觉了。你要哪里住？我想，我不知道有玩说，有可能病来问睡，那我就当时没有想，没有想，就没刷起来。因为看不懂我写的台词。那两个差不多。然后两个。我这个太腻了，没有写。应该是随便指导。
来，你赶紧两边。你给提供在搞。放，会放。
真的会分析，就是我也没有去理解。我也是吧。我会。
当时也给我们写这个信息，来学过。
直接写问第二题。我是有看我的实物，这边有不同采访。
前方面几个黄管，我就取代。
没有这个。
这个，
下一点，
这个。
那我给你，那我们
啊 oral test。这个。在这里。吃了啊。好餐。那个是好像打这个嘛。
拉的是我身体上的
伤疤来了，就打去的吧。
我应该看不到。
那我是考察一本，
那他不是有
具体的另外就感觉都慌了，我放进去了。天呐，我叫的完成他手机那儿，加一点味道。
我爹给我找。
没有的，会完成一个人项目那种感觉。我几个人吃了一个，
这个礼拜开吗？20个人。啊，你说这样啊？不是那个那个一个。好，谢谢。我不完这个。
我还背着什么比较强一点。
要接受。
对。
我给他吃的，再给嘛。
你没有先讲出来，你讲出来。那个跟那个也是兄弟啊。哎，
昨天不懂。怎么才把你切来？再让我去他去弄他那。
Hello. Okay, let's start. Start first. Start. Okay, so we will revisit alternating series test. So let AK is a bit different from how we formulate before. Let AK be a decreasing sequence, okay, of non-negative number. Converges to 0. The alternating series -1 to the power n plus 1 times an converges. How is this different to how we introduced last time? Do you remember how we introduced alternating series last time? I think there are 3 conditions, right? We need to check for alternating series. So let's remind ourselves what is that. So this is the how we formulated last time. Okay. So first of all, it has to be alternating. Second, what is it? Bn greater or equals to Bn plus 1 for all n. What does this mean? This Bn is non-increasing. But what we have just now is decreasing. No, not root test. How we introduce alternating series? It's decreasing. So what's the difference between decreasing and non-increasing? Huh? So meaning it might be equal sometimes, right? Might not be decreasing. Okay. And then the same same condition we had is the term Bn have to converge to 0. Okay, have to converge to 0. Okay, to converge to 0. Would there be any problem if we don't consider Bn equals to Bn plus 1 case? Would there be any problem? If Bn and the Bn plus 1 is the same, right? What happened? What happens if Vn and Vn plus 1 is the same? Should for some, okay. Me, you are the same number, how to say, with the next one, right? But what's the relation between the consecutive one? Plus minus, plus minus. So if you are the same as the next one, you will get cancel. So in the sum, you just get 0 in the infinite sum. Does it make sense? So we just need to consider decreasing sequence. If it is constant at some point, then the 2 points should cancel out. Does it make sense or not? 懂我在讲什么吗？如果你和你下一个是一样的，但是我们是 alternating series 哦，你们其中一个是加的话，另一个就要是减哦。然后这两个放在 series 里面会发生什么事情 ？cancel 掉，就会拿到0哦。这两个加在一起，对不对？这样就没有 contribute to 那个 sum 了嘛，对不对 ？Okay, so we just need to consider decreasing sequence. Does that make sense? 合理吗？How do you confirm they are cancel? They are side by side, oh. Sure. Infinity, what happened when you go infinity? You consider the partial sum. So in the partial sum, they will cancel. If they don't cancel in the first partial sum, you go to the next partial sum, they cancel out already. Make sense? You should have a sequence of partial sum that converge. This is the theorem. Okay, this is the theorem. Okay, does it make sense? Okay. Okay. So let's see how we prove this guy. So how do we prove this? So what we're gonna do is we will prove. Okay, so let's prove down what we want to show here. Okay, what we want to show is the alternating series converges. Okay, this is what we want to show. This is what we want to show, but what we do is we show for, so let some partial sum be written down. So let's this Sn to be the sum from k equals to 1 to n. Okay. So what we're going to do is we will compute the even term and odd term separately. Okay. Do you know why we want to treat even term and odd term separately? Why do we want to treat odd term and even term separately? Because they are the same sign. Let me think how to say about this thing here. They are the same sign. Not quite. What is the even term here? Even term means we add up to the term that is n with negative. If we take the odd xn, meaning we add up to the term that is positive. Okay, so this is the difference there. But let's see how it works. Let's see how it works. So instead, what we will do is we will first show that the even subsequence x2n converges. Okay, this is what we will do first. Then later we'll show s2n plus 1 also converge. Okay, then together we will have xn converges. Yes, that's what we have to establish later. Okay, that's what we have to establish later. Okay, so to this end, not that, x2n is what? Is the sum from k to n such that a to kn minus 1 minus 2k. Okay, so what's this here? Is this true? Is true or not? What is this sum here? See if this work. Huh? Correct or not? Let's see. Write down what is this? What is S2? X1 minus S2, right? Sorry. A1 minus A2, right? Okay. So in this case here, if you put 1 here, what happened? You have 2 minus 1 minus A2 times 1. Correct? Hello? Follow? Okay. About x4 is the sum from k equals to 1 to 2 of a2k minus 1 minus ak. But what is this? a1 minus a2 plus a3 minus a4. Okay, so this is the formula we need. Does it make sense? Okay. Okay, no? Following? Follow? Okay, so the problem is you want to write down this formula into this summation form. Okay. But what's nice about this thing? What is it nice about this thing here? So why do we want to write like this? Okay. So if you can, we can always pick up the first term. Okay. So here we have example. I took some example to keep in your mind what happened inside this formula here. So what can we do is we could consider the sum to be a1 minus k equals to 1, 1 and minus 1 to ak minus a. Sorry, a to the 2k minus a 2k plus 1 minus 2a n. What am I doing here? So I single out the first term and the last term. Okay, then I consider what happened in the middle here. Does it make sense? Okay, can follow? Okay. So what I want to claim here is this guy here is less than equal to a1. Okay, it's less than equal to a1. Why? A1 is the largest. A1 is the largest. Is it enough? Enough or not? A1 is the largest. Is it enough? I mean, to make sure this difference here is less than A1, what do you need to make sure? You need to make sure that A2n is positive. You need to make sure that the sum here is positive as well. Okay. So obviously A2n is positive, no? Because this is what we assume. How about the middle one? What is A2k minus A2k plus 1? The consecutive terms, even terms minus the odd term, right? But how do we minus? Do we take A2k minus 2? So do we take A2k plus 1 minus A2k or A2k minus A2k plus 1? There's a difference here, you know. Why is there a difference here? No, it's positive, right? There's non-negative number here only. Okay. So because AK always greater or equals to A2k plus 1. Decreasing, correct or not? Decreasing. But sometimes maybe how to say, they are non-negative, right? Okay, so they are non-negative, meaning it could be 0 sometimes. Okay, so we have an equal signs here. Does that make sense? Decreasing, decreasing. Okay, and also an greater than or equal to 0 for all n. So what we have established is this Sn here is bounded above by A1, by first term. Okay, bounded above by the first term. Moreover, what? Bounded above also want to suggest you to use some theorem if you want to say S2n is convergent. Bounded and what converge? Monotone. So is S2n monotone or not? Why? So why S2n is monotone? Decreasing or increasing for S2n? If you're taking sum or keep taking sum, supposingly sum of what? So this sum here is very special. This sum is actually sum of positive number. Why? We can group them as A1 minus A2 plus A3 minus A4 plus dot 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 out to A2n minus 1 minus A2n. Okay, so this is what? This is a sum of positive number. Okay, so what we have is this series is increasing, okay, and bounded above by A1. So that's why we look at S2n here instead of S2n plus 1. If S2n plus 1, what happened? There will be an extra A2n plus 1 outside. Okay, so that's why we look at X2n first. Does it make sense? Make sense or not? Okay, so by the monotone convergence theorem, the sequence X2n converges. Okay, converges. Okay, converges. But on the other hand, okay, how can we express S2n plus 1? How can we express S2n plus 1? S2n plus 1 is really just S2n at the last term. Add or minus the last term. Should be positive, right? Okay, because plus, minus, plus, minus, plus, minus, plus, minus, plus. So every odd term should be a plus term. Okay. So from this equality here, right, can you deduce S2n plus 1 converge or not? Can you deduce it? I know S2n converge already. How about this term here? Converge to where? 0. This is your extra condition here. This is where we use the condition that an converge to 0. Okay. So since limit of n to infinity of an is 0, then we can use property of the limit law for sequence. Okay, we can use the limit law of sequence such that limit of x2n plus 1 is equals to the limit of s2n. Okay, so they have the same limit. Does that make sense? So this part here, this is where we use the this part here is where we use the assumption. So this part is the assumption. Okay. Does it make sense? Question? Question? Okay. So this two limit is the same. We only prove that the odd sequence has the same limit as the even sequence. How about Sn? How about Sn? What Sn? How about the original sequence? Yeah, how to converge? Subsequent converge. No, right? We have a divergent sequence that subsequent also converge, right? So how to make the original sequence converge? The original is alternating. S2n and S2n plus 1 also alternating. Also alternating. We are not just picking the positive or negative term here. It's also alternating. Huh? I mean, we can let epsilon greater than 0. Okay. So what n we need to choose such that for all terms greater than n, xn minus x is less than epsilon. What n we need to pick here? What n we need to pick? Think about it. This Sn here, this small n here, what's the choice of n you can take? This choice of n. What n you can take? Integer value, right? Positive integer in particular. So what sort of positive integer? Even or odd. Either even or odd. So at some point, you will meet the even subsequence. At some point, you will meet the odd subsequence. Correct or not? But you know that even subsequence and odd subsequence all converges. That means what? There exists n1, n2 in n such that what? Such that S2n minus s is less than epsilon if for all the term greater than n1 and x2n plus 1 minus x is less than epsilon if n greater than n2. Okay, meaning what? For example, if n1 equals to 2, n2 equals to 5, meaning what? All the S4, okay? I mean, not S4, larger than X4, okay? You will get the distance less than epsilon. If 5, when n2 equals to 5, so all the S greater than 11, okay? In particular, like X13, S15, X17, all the different less than epsilon. For the even case, maybe S4, X6, S8, X10, okay? So together, what n you need to pick to make sure that the distance is less than epsilon? Huh? What's the n you need to pick here? Maximum of what? Not n1, n2, right? Because when is it true? Not S2, not S5. It only true starting S4 and S11. Because this is how we pick our n here, 2n plus 1 and 2n. So you need to start from 2n1 and 2n2 plus 1. Okay? 2n1 plus 1. So what you need to pick here is the maximum of 2n1 and 2n2 plus 1 here. Okay? Does it make sense? No question? Any question? Is it clear or not? Should be clear If not clear, you should ask. I don't know, but my experience with the student, maybe not this class, the other class, is they don't want to ask. They don't want to ask, they still don't understand. Okay, so please ask. Okay, I urge you ask. Okay, 求你问，好不好？如果不懂，请问。Yes. This is the conversion that we established just now. We found the limit of 2n, S2n, and limit of S2n plus 1. 这是什么意思？ Because what we have proven first is, what we have established is we first proved that S2n converge. Where is it? What we established is this one first. We established S2n converges. Why we don't want to apply to S2n plus 1 is, remember how we established this convergence here. We need this sum to be a sum of positive number. Okay. And also, this term is bounded by, this S2n is bounded above by A1. If you add S2n plus 1, what happened? There will be an extra A2n plus 1 here. Correct or not? There will be an extra A2n plus 1 here. And then this A2n plus 1 here is depend on n. But when we want to show boundedness, right, we don't want to depend on n. Have to be true for all n. Okay, so this proof for S2n to converge cannot carry forward to S2n plus 1. Cannot carry forward. Okay, does it make sense? So we cannot prove S2n plus 1 converge using the way we prove X2n. So how do we prove X2n plus 1 converge then? We express S2n plus 1 using X2n and the last term here. Then in this case, we can show that X2n plus 1 converge. Why? Because it is the sum of two convergent sequences. Because it is a sum of two convergent sequences. In particular, X2n converges and A2n plus 1 converges to 0. So the sum of two convergent series is what? The limit of sum of two convergent series is the sum of limit of two convergent series. Okay? Does it make sense? Okay. Yeah. Question? Ask. Ask. Yes. Scroll up. Scroll down. Okay. Yes.
Why you conclude that
Oh, okay. Sorry. There's a typo here. So what we conclude is we only conclude for S2n. Yeah. We only conclude for S2n. Yeah, there's a typo here. Okay. Yeah. We only conclude for S2n. We haven't mentioned Sn. We haven't mentioned S2n plus 1 also. Correct? Yeah. We only start mentioning S2n plus 1 starting here. And then we will link it to Sn. Yeah, that's a typo. Question? Other question? Okay, can follow everyone? Please follow. Let me tell you a story. The department now are actually facing a problem. What problem, you know? Problem with communicating with students. You know what this problem causes? It causes problem in their FYP project. What problem is that? The supervisor cannot contact their student. and their student don't report to their supervisor. This is the problem. Because you don't interact with your student in the class. So you have to keep interacting with your lecturer. If the lecturer don't like to interact, then that's the problem of the lecturer. But whenever you can, you should interact with your lecturer. Yeah. Okay. Yeah. If the lecturer don't like it, then that's the lecturer problem. But whenever you can, please interact with your lecturer. Okay. Any question before we move forward? Last one. Yeah. Yes. Zero. I don't care whether it converges to zero or not. And it won't converge to zero, right? Okay, it can. I mean, yeah. Wait, why you care about where it converge? Okay, I don't care where it converge. It converge to something. Limit. Yeah. Yeah. Okay. Okay. Any more question? More question? No? Okay, if no question, I think we will go on. Let's see how much we need to go. Okay, maybe we'll finish up the new two tests. So, like what I said, so alternating series test is the last test we did in Calculus 2. Okay, so this is the last test we did in Calculus 2. So we have proven all the tests we have used in Calculus 2. So now we're gonna do Dirichlet test and Abel's test. Okay, and I will show you one example that one of them apply but not the other. Okay. But before that, should we do the lemma first or not? Before that, we will do this lemma. Okay. This lemma is called summation by parts. So summation by parts here, you can relate it to integration by parts. Okay, let's see how this is closely related to integration by parts. Consider AN and BN. Okay. Consider AN and BN be two sequences of real number. Okay. Let M in N. 来，诗音啊，我现在在教你要讲的东西啊。如果你能听的话，听一下。Let Bn to be the sum from k equals to 1 to bk for all n in n. Okay. Then, okay, so this is an important result here. You see how I have two sequences here, AN and BN. Okay. So what I do is I want to sum the product of these two, AK and BK. Okay. AK and BK. Okay, sum of these two products. So if you want to relate to by parts, right? What happened in by parts? You integrate FG prime, something like that. FG prime. Okay. So I mean you can think of this sum as integration. Okay. So what I got is AM plus 1 BM. Okay, so you see differentiate this small n and big B. What is big B here? Big B is the sum from 1 to m, for example. Okay, the m partial sums minus AN BN minus 1. Okay, so what's the relationship here? AM plus 1 is the extra term. Okay, then this AK here, and then BM is the last partial sum you can see from the product of AK and BK, the sum of product of AK and BK. And then AN is what? AN is the starting point here. Okay, and then BN plus 1 is the sum from 1 to n minus 1. Okay, so you should think that, about the middle term? What happened to the middle term? So we take minus sum from k equals to n to m of AK plus 1 minus AK on BK. Okay, so this is the summation by parts here. Summation by parts. So I give you a task. If you don't appreciate this number, right? So I give you a task. So try this sum. Okay, using say n equals to 2, m equals to 4, something like this. Okay, try and expand it. 听得懂我讲什么吗？那 n 等于2 m 等于4，把全部东西给我开完了，你就会看到这个东西了。Okay, but when I want to prove it, I just prove it in general. Okay, general 知道什么意思吗 ？General 意思 ，general 什么意思？笼统。Okay, 笼统 ，yeah, 笼统。Okay, so if you want to see this sum, take n equals to 2, m equals 4, expand it, 把它开掉。OK， 你就会看到为什么这个是对的。OK， so we will prove it in general. Actually, this proof is not too hard. Okay, but to think about this proof is a bit tricky. Yeah, a bit tricky. So what we're gonna do is we're gonna study this part first. AK, BK. Okay, we want to write AK, BK into a form using this partial sum. Okay, this partial sum here. 来啊，子英，你是写这个 proof 还是写我的 proof 啊？还是写 Jack 的 proof？Jack 的 proof 啊？那比较短。OK， 这个更短。啊，你来看看。OK。Okay, so the problem is that we want to write AK, BK in terms of this partial sum of Bn. Okay, in terms of partial sum of Bn. So note that little bk is simply capital BK minus capital K minus 1. Correct or not? This one is by definition. What is capital BK? Adding I equals to 1 to K. Then capital BK minus 1, adding 1, B1 up to BK minus 1. Okay? Okay, so this one is by definition. So this implies what? AK, BK is simply the sum of AK, BK, capital BK, sorry, minus AK, capital BK minus 1. Okay? Make sense? Okay or not? So what do you anticipate next? What should I do next? What am I interested in is the sum of AK little bk. Okay, AK little bk here. Okay, and then I can sum on both sides. I can sum on both sides. 合理吗？现在，子英，合理吗？子英合理吗？子英？就加不了嘛，每一个 term 我来加在一起。Okay. So what do we get? What do we have now? What we have now is we already got this term. We already got this term. This one. This part we already got it. Which is the first term here. Sum from n to m AK BK. Which is this term here. I circle. Okay, so what do you left with? You left with the other three terms now. Okay, so you need to show that the other three terms is formed by the last term here. Okay, so this is the last term here. So you need to show that all the rest have to build up using the last term. Does it make sense? Can see? Okay. We already built the red term, but the rest need to build using the green term. Make sense? Okay. So how are we gonna play with it? So what term is easy to drop out? Which term is gonna drop out first? So let's try. So let's start with the green term. So what's the green term? Is the sum from k equal to n of m, ak, bk minus 1. Okay. So which term is easy to drop out? Huh? You see, what's the first term here? an and bn minus 1. an and bn minus 1 is one of the things that you need here. Okay. It's one of the things you need here. So you can pull it out first. Okay, let's pull this guy out. So we get an, bn minus 1. And then, what's the last term here? What's the last term? an, bn minus 1. Wait, is this what you need? Not quite. Not quite, huh? But the last term is what? Am and bn minus 1. But you want this term, so 我要哦，怎样办？妈，我要这个玩具，怎样办？叫你妈给你啊，对不对？把它加进去，加进去罢了。OK， 加进去啊。I add it in. Sum from k n minus 1 to m plus 1 of ak bk minus 1. 所以你加进去啊，你一定要补回来的嘛，不然潜水去撞，对不对 ？So you need to take away am plus 1 bm. Okay. Good. Are we done? Done. Are we done? A bit different, a little bit different. Where's the different here? A little bit different, slight different. Okay, let me copy down. What's the term we need? M of AK plus 1 BK. Okay, this is what we need. So let's compare what we have at the back. So copy, cut. So this is what we need. A plus 1. Okay. What's the difference here? Are they the same or not? Same or not? One start from n. One start from n plus 1. One start from m. One start from m plus 1. What's the difference? 一个是2，一个 start with 2，一个 start with 3，一个 end with 6，一个 end with 7，什么差别 ？Yeah, one step more。但是里面呢？里面发生什么事情 ？One step more 的里面 consider 什么 ？AK 跟 BK 减1。One step less 的呢 ？AK 加1跟 BK，K 加1跟 K 什么关系？少一个 ，K 跟 K 减1的关系又少一个，谁多谁少啊，很重要，那个谁多谁少很重要。OK， 把号码丢进去看看。哎，我好像有点白痴，是不是？什么叫做 n 等于 n？k 等于 n。Okay, so on the left hand side, green term, what's the first term? an plus 1 and bn. Right hand side, an plus 1, bn plus 1 minus 1, n. Okay, so they start at the same point. You also can check that they end at the same point. So meaning what? You are just doing re-indexing. So you just re-index. Okay, you just re-index it. So when you re this, you instead start from n plus 1, you can start from n, but what you do is you increase your indexing. Okay, you increase your index. Okay, and then you end with n. And then so this is what we want in our formula. Okay, no? Hey, but the sign is a bit different. Why the sign is different? Because we are considering the negative of the sum of AK capital B capital. Okay, it's a negative of it. Okay, so then the result follows. Okay, no? Question? Or question? Question? 问题来？问题吗？数学就做一个工作罢了，有问题解决问题，就是你在这个数学系可以得到的东西。如果你读了数学系还解决不了问题 ，then 你就是还没有毕业。OK， 你要从数学系毕业，就是有问题解决问题。所以为什么你们有这样多assignment做到你头这样痛，就是为了你天天解决问题，天天。你一定要解决问题，你能够解决问题，你才可以从数学系毕业，好不好？数学系数学家就是为了解决问题吧，解决世界的问题。OK， 有问题吗 ？Yes， Yes， 听不懂？哪两边？青色的部分 ，This part。或者什么叫两边？这一个跟这一个哈啊，对呀、这个跟这个没有，这个是我。This one is what we. I mean, wait, what are you doing? Oh, wait, sorry. So this okay. So what I want to claim is this two orange box is the same. Only these two orange box. Okay, that's all. Not the thing behind. The thing behind is what we wanted, right? So we don't need to care anymore. Okay, what we care is this looking weird term here. Because in the statement we want this. So how is this sum here related to our sum? I mean, yeah, our sum in the statement. So what we do is we just relabel it. Does it make sense? We just relabel. It's exactly the same term if you expand the sum. Correct? So we just relabel it. Okay. Question. Relabel. Reindex. 你想 re 什么？最后第二个，最后这个 relabel。reindex。index 是什么 ？index 是这个 k。reindex 就是说我重新编号，就是说怎么说啊？给我想一下怎么告诉你。Okay, first of all, do you agree that they start with the same term？ 是不是重新一样的开始？但是它的区别在哪里？它区别是我怎样去把这个 k 的号码放进来，对不对？第一个的时候我放 k，A 那边我放 k， 第二个我放 k 加1，对不对？懂什么意思吗 ？reindex 啊，重新，对啊，我觉得左川讲的没有错啊，重新编排，就是给它一个新的名字，讲新名字很奇怪，就是 reindex 哦 ，reindex 这句话就概括了，其实，所以那个听的人应该要知道什么叫做 reindex。reindex 就是说我重新 很短哦，Yeah， 很短，Yeah， 很短。但是你怎么想到这个东西，其实是蛮长的一件故事，只是说的时候可以很短，因为平时应该不会想到这样的东西。好，OK 吗？Yeah。Okay, I think we should need to do some more proof. Should we do proof or take a break? I think it's better to take a break here. Okay, so maybe I leave a few words on this theorem here. So how nice is this theorem? Nice is this theorem here. So you can see that later we want to look at a series of product of term. Okay, we want to show this kind of term converge. But what we know is we know the condition on sum of Bn and we know the condition of An. That's all we know. So what this summation by parts doing is I split the sum of product of term into what? Into a product of An times a sum of Bn. Because later we will have condition on Bn. Okay, and An also. Small an and capital Bn. This is the condition we will have on our series later. Okay, that's why we want to split into this particular form here. Does it make sense? Because you can imagine 啊，你也可以想象嘛，感觉这个什么啊，这个 formula 很 symmetric 哎，你觉得 symmetric 吗？我不一定要小 n 跟大 B 嘛，我也可以是大 A 跟小 B， 对不对？可以的吗？有问题吗？我可以写一个 formula 给大 A 跟小 B 嘛，对不对？是不是这样讲？I mean 我只要 swap A 跟 K 就好了嘛，我也是拿到一样的 formula。但是为什么 ？Why we care about small a and big B? Because later the theorem we will have condition on capital B and small a. Okay, later we will see how we gonna use this theorem here. Okay, so 现在啊，我 present 数学给你的方式有点不同，有点不同是什么？我是从一个3D 视角来跟你讲。什么叫3D 视角？我已经预知了我要用什么东西，我先跟你讲讲。OK， 这个是3D 视角。OK， 我先做掉我需要的东西，我再跟你讲怎么用它。Instead of 我先去做，做不到了，我再去 prove 一个小 lemma， 但这个东西就变 lemma， 所以我写 lemma 先。我先做一个东西，但是 prove 不到 ，OK， 我先 prove 一个小 lemma，prove 了小 lemma， 我再回来 prove。OK， 所以有2个方式做数学。OK， 一个是我已经知道了，我先跟你讲；另外一个不知道，我们遇到问题我们解决当场，明白吗 ？OK， 说现在我 present 的方式，你应该在你的脑里面就要想，哎，怎么 NgeKieSeng 要 prove 这个 lemma 的？应该要想，哦，这个 lemma 可能等一下要用，你明白吗？是这样子想，而不是想，哎呀，怎么要做这个 lemma， 怎么要做呢？不是，你应该要想，这个 lemma 应该是等一下要用的。OK， 等一下我们就用它。Does it make sense？ OK 吗？所以你听数学的讲座或者人家讲话就是这样。OK， 你要听一下，为什么这样讲？可能他下一步就要用这个东西，可能就是为了他未来的事情铺垫的。哎，这个很合理啊，很合理啊。你回去干崩不是？你回去听你爸爸妈妈讲话啊，可能你问你妈，怎么这样生气？OK， 他不会跟你讲为什么他这样生气了，他跟你讲，哎呀，早上那个啊什么啊，你爸啊什么这样啊这样啊这样这样这样，那个是他雷妈，对吗？他的雷妈吗？因为这个雷妈发生了，所以他才生气吗？明白 ？Theorem 啊，明白吗？明白吗？这是他雷妈，所以你要听清楚他们的解释，你知道吗？雷妈很重要，你明白吗？雷妈很重要，明白吗？OK。 他不会直接跟你讲为什么他生气了，他就跟你讲哦，那个人啊敲到我，还是我早上去买菜还是什么之类的。哦，然后是雷嘛，然后听清楚那个雷嘛先，OK OK 啊，OK。So later we'll continue with Abel test and usual test. So we'll resume at 209. There's some more snack here if you want to take. 还有。
这个XK 它有就求的就会的，这个就是一些 N 加深，但是就是全部都是。那你什么意思？一个东西。哦，这2就不算了，但那不是的话，我觉得X3在这边，知道吗？这其实 N 跟 B 好像是有。N 的为什么说有？可能在这个学期的就一天前吧，就一天前了，学期。
找到另外一个
发过来给
发不同要圈，
可以。
因为我就直接从那个文章里面截出来。
不要单截那个，你要截它的前面啊，不然的话我看不懂前因后果。但是你要圈一下你看不懂的地方啊。对。
，yes，
他们全部都不一样。
属于不一样。
是一个 M1、M2相差。
不然的话你得不到，就是你得不到全部啊。
最多对。但是我的 M1 有跟 M2，我的 M1 跟 M2，他们都有一样的东西，
所以是 M 也是
M1
啊。
那 M1 有你 M2 来。
那个本来就蛮是这个真死，
那你的 M1，如果我玩什么，说的话，我对的，但是其实相对讲的话，那你 M1 就会有个基因，就是会丧失。
现在有上帝宣教是有一点，
是我才我想零。
然后我要玩
是这个东西，你两个的话，对。还是有鱼的。对对对对，它里面它的银河不，它的银河不是有些比较的，里面有这些天地跟storm，它的银河不是。像我讲这里啊
，MBA 香蕉不用紧啊，上次就是 M 是一个。
下一个去吧，跟下一个是不一样。
我想后存不准，因为你去加啊，加你的唯一下来，或者不准，对不对？
这是我感觉M10全部都跟下一个
问题是你的期待，对，有一个他了一点，你主要是
没有你，我觉得你现在不知道那个2N加1是从哪里来？
知道知道，哎，然后先减一个把这种生，哎，
减一个，对，从
这样有点真的是，有点难，有点难。
你从这边一个一个，对，一般啊，然后有这个，一个一个
，OK，那我给你一个方
我已经给了，我就写了，这个从这边我就推出来。哦，
9个钟是吧？是不是5乘2点？
它变，我说的，它变，那是。啊，因为把这个这个嘛，对这个嘛，这个经典。
general 要讲话，
安全的人，
以前 argue，
我 argue 就是这个东西哦。
没有这个，你要讲有跟这个是什么？我就是遇到现在，
我现在跟你讲，我所有的OC，所有的全部都是这样子，就是两个 FT。
所以你现在假如方式不错，是因为解的关系。你用你这个方式来再解释一个解，用你这个方式啊，用这套去解释为什么这几个话有因为啊，为什么这个情况？可以到是一个反的，就这个情况。的话，我是想也是这一行不当你的什么 S 在2K 正常的哦。
这样我是要跟你讲我的习惯，这样，我这样是不是就把我的习惯是 小数大这个分析哦。S 2就会在这个生产 X3会等于这个我这一。
OK，解答。
对，
我觉得我觉得
S5也会等于3，就S7是会等于出。
好，可以了，听懂了。好，讲用这一套东西找个11个东西，
找11个东西，
找11个，
用先花
要用这套理论来跟你讲。
这套理论就是这个东西。
这点罢了吗？我要加你 OK， 跟着你这个解释加了一些点进来帮你猜到。
没有，我没有加一点。是。
你的 S 多不对 ？OK。
哎，我的 S2啊什么？
加了点过后，讲找这个 general 的，不要画，用讲的，用你这一些点讲一讲。
哦，点啊。像我这样在，就是如果大家打了可以加1，会等于这个就讲我的题对这个这个题3会等于的。如果我可以看到一个 pattern 吗？
pattern。
但是我想回去那种刚才
我先开始啊，等下再讲。Hello, testing. All right. Hopefully we can finish different series today. So first new test we're gonna introduce is called the Abel's test. Okay, Abel's test. So Abel's test says what? If you know that a series, okay, converges. Let's say BK, the series BK converges. Okay. And a sequence is monotone. Okay, so this sequence is AN, is monotone and bounded. Monotone and bounded says what? The series of AN should converge. Correct or not? Okay. Then so BK already converged, right? I won't ask question about BK already. AN is monotone and bounded, so the series also converge. So what's the problem here? So the problem here is we want to look at the sum of AK, BK, product of them. Okay. You want to guess what's the result here? What happened to this product? Sum of this product. So individually they converge. But when we consider the product of them, also converge. Okay, so this is the content of Abel's test. Make sense 吗？明白吗 ？Abel's test 啊 ，so 这个很接近 division test 啊 ，OK Abel's test。Everyone can follow？ 可以明白这个 test 在做什么吗 ？You know that sum of BK already converge. AN converge, but we know that it is monotone and bounded. Okay, monotone and bounded. Only the sequence conversion series, not sure. Series not sure. But the sequence itself converge. Correct? Not? Monotone convergence theorem. Correct? Okay. Sequence itself converge. But in the web, in the alternating series, the term converge to 0, right? Okay. But here only convergence. So if you have an AN that converge and then a series BK converge, you can consider the product of them. Okay, the sum of product of them. And then the result is they converge also. Abel's test says conversion. Okay. So to check this kind of series, what do you need to do? If you want to prove this kind of series converge, what do you need to do by Abel's test? You need to test that the infinite series of BK converge and AN is monotone or unbounded. No, unbounded. Yeah. Okay. So if you can prove these two, then you can show this kind of series converge. So how do we use the lemma just now. So you want to show a series converge, right? What do you need to show? You need to show the partial sum converge. But yesterday, we said that when you want to prove a sequence of partial sum converge or sequence of real number converge, what do you need to show? You can show that it is Cauchy. Okay, you can show that it is Cauchy. So actually, what do you want to show? So prove. So you want to show that for every m greater than n, Sm minus Sn minus 1. So I want to show that for every epsilon greater than 0, there exists an n such that for all mn greater than n, Sm minus Sn minus 1 is less than epsilon. Okay? You show that it is Cauchy. Does it make sense? But 什么是 Sm 减 Sn 减1啊？这个情况，这里的 partial sum 长怎样？什么是 Sm 在这个情况 ？Sum of k equals to 1 to m ak bk minus sum equals to k equals to 1 to n minus 1 of ak bk. Okay, but what is this? Sum from k to k from n to m. But just now the lemma says what? This number here is equals to am plus 1 bm minus an bn minus 1 minus sum of k equals to n to m ak plus 1 minus ak times bk. 这个东西刚才 lemma summation by parts 给了这个东西 ，OK？ Then 我们可以用 triangle inequality 来 bound 它，对不对 ？So triangle inequality 怎么 bound 它？我可以直接带进去，看到吗 ？We can use triangle inequality here. Everyone check whether I use the right inequality and triangle inequality or not. Yes. I mean, if it's equal, then the sum should be just 0. Correct or not? If it is equal, then it's sum 0. I mean, not much difference. Not much difference. Yeah. If m equals to big N, if m equal to big N, n equals to big N, then yeah. Okay. I mean, yeah. Okay. Sure. So what do we have here? We split the difference into how many absolute value? Into 1, 2, 1, 2, 3, 4, 5, 6 like that. Okay, 1, 2, 3, 4, 5, 6. Why we split into this term? What do we know about an? An is monotone and convergence. Sorry, monotone and bounded. Meaning what? This term should converge. An should converge. Okay. An should converge. Converge to where? I mean, bounded is good enough. Okay. So what do you see? Here is bounded. Okay. This one, this one converge. Converge. Bn converge. So what is Bn here? Bn is the partial sum for Bk. Okay. Bk converges, partial sum also converge. So this one bounded, this one converge, this one bounded, this one converge. And then this Bk also converge. So how about this part here? What is ak plus 1 minus ak here? And what is this part here? absolute value some more. Okay. What do we have about AK? We already used boundedness. We left with monotone. So assume maybe increasing or decreasing, non-increasing or non-decreasing. Let's say non-decreasing. Okay. So what happens if AK plus 1, AK is increasing, non-decreasing? So suppose without loss of generality, AK is non-decreasing. What happened? So AK minus 1 should be less than equal to AK, less than equal to AK plus 1, and then so on. Correct or not? So, what does it mean by you add up the difference between consecutive terms here? What does it mean by adding up the difference between consecutive terms here? So what does it mean by adding up, say, AK minus 1, AK minus 8, sorry, AK minus 1 plus AK plus 1 minus AK. What is this? This is, what is this? This is exactly AK minus 1 plus AK, let me see whether I'm correct. Yes. So this is plus AK plus 1 minus AK. But what is this? This is exactly AK plus 1 minus AK minus 1. Okay, so what you left with is the difference between the first term and the last term. Does it make sense? Okay, this is not true in general. If it is not monotone increasing or decreasing, it's not true. Because your difference can have overlap. But now there's no overlap. Right? This is non-decreasing. Okay, there's no overlapping here. Okay, in general, this is not true. You cannot have the first term and the last term equal. I mean, the sum of the difference is not the difference from the first term to the last term. Okay. So what do we have here is, let me write down first. So this guy will be, let's see. So this guy will be equals to the sum of A and B1. Bn plus An of Bn minus 1 plus sum of Bk times absolute value of Am minus, sorry, Am plus 1 is it? Yeah. Am plus 1 minus Am. Okay. Yeah. Does that make sense? 明白吗？可以明白吗？问题，不明白要有问题。Any question? No? Okay. Question or no? Yeah. Okay. Yes, question. I what? What I what? Yes. Oh, yeah, you are right. So, I mean, so, okay, so we need to be a bit careful here. So, careful. So, we apply triangle inequality to the fullest. So, what do we mean by fullest? So, we have bracket here.
Okay, we already bring my BK outside already. Then does it make sense or not? Does it make sense? Oh, sorry. Cannot. Sorry, cannot. So I mean, before doing that, we have some trick actually. So we can't quite write like this yet. So I think you are true. Okay, we can't write like this yet. So what we know is, okay, we cannot write this equal first. Before that, what we know is only n, the sum of k from here is equals to, sorry. So, okay, so we treat it separately. So we haven't quite replaced that the last term yet. So we just compute this sum first. Okay. Yeah. So this is the two pieces of information we have for now. Okay, for now we have this two pieces. We cannot bring the BK out. A bit troublesome here. Why? Because this BK is depending on this sum here. So I cannot simply bring it out. It's not constant. Okay. If it is constant, then I can bring it up. Because this BK will grow when the sum grow. Okay, no? Yeah. So I cannot bring it up. So later we need to do some trick so that we can remove the dependency of BK. Okay. So is it okay so far, everyone? So far, okay? Okay. So how we bound then? Okay, this is the job now. How we bound all these guy? Okay, how we bound all these guy? So let's do the job. So we have a few conditions. We have few conditions. So now our goal becomes showing Sn is Cauchy. Okay. So if you want to show Sn is Cauchy, let's give us some epsilon first. So there are few conditions, right? We will use all the conditions, in fact. Okay, we will use all the conditions. So let's see how we use it. So first of all, this BK, this infinite series of BK converges. Okay, so what happens? It converges. Then there exists M1 in R such that for every n in n, this partial sum should be less than M1. Okay. Why? Because if you converge, then it means that it is bounded. Okay, so we want to bound the partial sum. Make sense or not? Last time we have shown it. Yesterday we have shown it. Okay, it is bounded. We want to bound it. Okay, we want to bound all the partial sum. Okay. A. What should the M1 be? Yesterday we say. What can M1 be here? What can we take for M1 here? Yesterday we already say. If a series converge, what can you use to bound all your partial sum? What's the sum itself? Just take the sum itself to bound it. Just take the sum itself to bound it. Okay. Is it true? Is it true? True or not? I think not quite true in this case. Yesterday, why true? Because our series is positive term. But today, not, maybe not. Can you imagine one condition? How you convert to this sum? You converge from above. Okay, you maybe converge from above. Then for all the infinite terms you in the tail you take is negative maybe. Okay, so today is not quite true. Okay, yesterday we have positive terms, so it's okay. But now not true. But anyway, we have bounded by some number because purely because if a sequence converges, then it must be bounded. Okay, so this one is in this case here. How about second case? Second assumption, what do we have? We also have an is bounded. Okay, so if it is bounded, then we try and bound it as well. So there's this M2 in R such that for all n in n, the absolute value of an is less than or equals to M2. Okay, we bound these two terms here. Okay, right. So now we want to pick the largest bound here. Okay, we call it M. Okay, we call it M for this one of these two terms here. We call it M. Okay, so what we're gonna use this n for? We're gonna use this n to bound our convergence of our partial sum. So we can set epsilon to be epsilon over 4m. Okay, so that we can bound our partial sum from k to n, bn, take away the infinite sum here. Okay, does it make sense? Okay or not? So we're gonna use this capital M to make a epsilon to bound the convergence. Is this allowed? Allowed, right? Because our series converge. Okay. So later you will see why we pick this epsilon over 4m here. Later you will see. And then what else? I think we need one more piece of information. So an is bounded and monotone. Meaning what? Monotone. Meaning by MCT, it is convergent. Okay. Even if it is convergent, it is Cauchy. If and only if Cauchy. Okay. So we're going to use Cauchiness of it. So how to use this Cauchiness? So there will exist an n1, n2, such that for all mn greater than n2, am minus an is less than epsilon over 4m. Okay. Also, we want to make it smaller than this number, and there's also one number we want to make it smaller. So we can set another epsilon. Okay, we can another epsilon. So maybe it's a bit crazy about this epsilon here. So what's this epsilon? This epsilon is epsilon over 4 times the sum of n equals to 1 to infinity of bn. Can I do this or not? Can I do this? What is this sum here? This sum converge, right? Just a number. Okay, it's just epsilon over 4 times the number. So these two numbers might not be the same. Correct? One is 4m, one is 4 times this sum. So there might be two different n that can realize this epsilon. Because an is Cauchy. Cauchy says what? For every epsilon, there exists an n. So there are two kinds of epsilon here. So there might exist two different n. No? Does it make sense? Okay. So, right, now we need to do our business already. So we want to show that Sn is Cauchy. Meaning for every epsilon, I need to find a capital N. So that Sm for all mn greater than n, Sm minus Sn is less than epsilon. Okay, so what's the n need to choose here? So there are how many n we have now? We have n1 to make sure my convergence of to make sure the convergence of my partial sum of Bn, n2 to make sure my Cauchiness, n3 to make sure another Cauchiness. Okay, so obviously I want all of them to hold true. So meaning what? I need to choose the maximum of 3 of them. Okay, I need to choose the maximum of 3 of them. Okay, later I will show you a magic on how to use all these. So if I choose the maximum of this guy, now let mn greater than n. Okay, so we will have all the computation. What is Sm minus Sn minus 1 here? So let's bring our computation down. So we bring this down first. Maybe not bring this one down. Maybe bring this down. Okay, bring this down. Copy. Yes. Okay, let's bring this computation down. All right. C. Okay. So, yeah, what are we gonna do? So what we're gonna do? We have all these n. What are these n for? So let's see what we have. We can bound the individual term, first of all. I mean n partial sum for Bn. And we can bound An. Two things I can do now. What's the third thing? I can bound partial Bn with infinite series here. Okay. And then I can bound the Cauchinus of A and B. So there are 5 epsilon. So 3 epsilon and 2 m bound I can use here to bound this giant sum. Okay, so let's see how we're gonna use it. How we're gonna use it? A bit challenging here. How we're gonna use it? So what we're gonna do is I will introduce B infinity in first. Okay, so we'll introduce the term minus a b n plus 1 of b infinity. B infinity meaning I add to infinity. Okay. And then, of course, I need to add it back. And then I can compare with a n b n minus 1. Okay. Yeah. Because I need to bring the epsilon in. If I simply use this m, then you will have, how to say, if you just simply bring the absolute triangle inequality in here, what do you get? You get m1, m2. There's no epsilon here, correct or not? So I need to bring in b infinity for me to get the epsilon here, correct or not? Okay, I want to bound by some epsilon. And then, what's next? Feel like not enough, feel like not enough. Because if I can factorize here, I couldn't factorize here. How could I factorize an plus 1 and an? Because what my plan is, I want to bring epsilon in using b infinity and bn minus 1. Or not? Okay, because I can make the partial sum of bn very close to b infinity. But here, an and an plus 1, I cannot factorize. What do I do? Add another term. I add another term. What's the term I need here? An b infinity plus an b infinity. Okay. And then what's next? The rest I will keep it. So I'll keep this sum here. Is it? Let me see. Yeah, I'll keep this sum here. So I'll just keep this here. Okay. So what's next? So I can use triangle inequality now. Okay, I can use triangle inequality where I break into like this. An plus 1 times an minus b infinity plus an plus 1 minus an times b infinity, right, plus an times b infinity minus bn minus 1 plus, what's the last guy here? Sorry, should be, yeah, plus what this last guy here? Sum from k equals to n to infinity of a minus 1 minus ak times bk. Okay. So put more sign here. Okay. So now we're gonna use the 5 condition we have: m1, m2, and 3 epsilon. Okay. So how can I bound am plus 1? I bound am plus 1 using m2. Okay, using m2. But I pick m to be the largest of all. So simply, if you are bound by m2, surely you bound by m. Okay, because I pick m to be the maximum. So I have an m outside already.
What is Bn minus B infinity? We pick it to be epsilon over 4m. Okay, good. How about Am plus 1, Am plus 1 minus An? This is the Cauchy part. Where is the Cauchy part we pick? We pick it to be either epsilon over 4m or epsilon over the sum here. Okay, so which one is useful here? Which one is useful? So in this case here, we have this B infinity. So the useful one will be epsilon over 4 B infinity. Okay. Times B infinity. Good. And then what? What's next? You want to tell me what I'm gonna do? Again, An is less than M. B infinity minus Bn minus 1 still epsilon over 4m. How about the one behind? For every k, I can bound it by, how can I bound bk? Also by m. Okay. Also by m. So you see, what do we get for the first few term? I get 3 epsilon over 4. So what you want to guess for the last one? Should be epsilon over 4, right? So how this epsilon over 4 pops up? So what do we show about this sum here? This sum here. Now we can use our sum to be the last one, take away the first one. Okay, where is this? Okay, this one. So we have An plus 1 minus An times m here. But this part is a Cauchy part. Cauchy part says what? It is less than or equals to epsilon over 4m times m. So you get epsilon over 4 here. Does it make sense? Okay. Okay. So I mean, so you think why we want to pick this epsilon over 4, epsilon over 2? Why we pick like this? Because this will help us to keep track where we use epsilon. How many times we use epsilon? So actually here we use 4 times. Okay, twice from the convergence of Bn, twice from the Cauchiness of An. Okay, does it make sense? Okay, so this is Abel's test. So now we will invite Sing to tell us about directional test. 可以吗？准备好了吗？还没有。OK， 明天。Okay, any question about Abel's test? Any question about Abel's test? Question about Abel's test? Yeah. Is 530. Less than or equal to m. Let me think. B infinity is less than. No. Because this is just let me see. This is how we pick n. Okay, we pick the capital N so that the Cauchiness will less than these two numbers. Either one of them. Yeah, either one of them. So if you take n large enough, it will satisfy these two conditions. Correct or not? If first one you can satisfy after 100 terms. If second one you can satisfy after 200 terms. Then I just pick 200 terms, then both of them it will satisfy. Okay, doesn't imply the relation between B infinity and M. Okay, it just says that the Cauchiness can satisfy this epsilon property, these two epsilon property. Yeah. Bounded above.
Yeah. Yeah. Mm-hmm. Oh, this one, yeah. This is the convergence of partial sum. Mm-hmm. Yeah, think so. Scroll up to when? Up to scroll down to entry. Entry, yeah. Yes, we did use entry, right? We use entry in this step here in particular. This step. We use entry here. We want to make sure the Cauchiness is less than epsilon over 4 times that sum. Because that product's there attached to the infinite sum of B n. Right? So I have to cancel out that constant. If I cannot make my Cauchiness cancel out that constant, then how? I cannot control that number. Does that make sense? Yeah. So you see, the problem here, where's the problem here? So the first M is to control, so this M is to control this AM plus 1. Okay, so we should go like this better. And then this denominator here is to control this B infinity here. Okay, yeah. And then M again control AN. And then BK also have an M to control it. Okay, remember we pick M to be a maximum of M1 and M. Okay, so there are M2 that control. Okay, is everyone satisfied? Long, later we will see another long proof, but not important for arrangement. For arrangement is also long. But so far okay or not? So far okay. So far so good. Okay. Okay. Yeah. Very long calculation. You just drawing diagram. Yeah, you can try. You can try. You can try. You could try. But what I want to say is we use what have we used? We have used boundedness, we have used convergence, okay, and then Cauchiness. So we're putting all the ideas together inside this proof. Cauchy, bounded, convergence, okay, and then pick the right epsilon to work. Okay. I think it's quite delicate, I would say. Quite delicate. 很缜密。很缜密。很缜密。选到很美。In the end, we still left with epsilon. Okay. Yeah. 很缜密。Oh, right. Right. So this is about Dirichlet test. How about sorry, this is about Abel's test. How about Dirichlet test? How about Dirichlet test? Okay. We'll say that if the sequence Bn is bounded and the sequence of An is monotone and converge to 0, then the series of AK, BK converges. Okay, so I think we won't prove this Dirichlet test. If we can, next time we ask Ying to prove here. Okay, I mean, this proof is a Q3. So, I mean, this proof is very similar to what we had just now. What's the difference? Just now, our Bn converged, but in this case, Bn only bounded. Don't know converge or not, but bounded. If monotone, then converge, but just bounded in this case.
AN then? Monotone, same. We have monotone. But previously we have boundedness. But now, straight away tell you it converges to 0. So meaning it is monotonely increased to 0 or monotonely decreased to 0. Okay, 2 cases only. Okay, and then the result is AKBK converges. The proof is similar. It's similar. Actually, this proof is easier because you directly deal with Bn. Just now you not directly deal with Bn. And this epsilon, this An converge to 0. You know. Hello. Okay. So you see, I can straight away directly deal with this term here. You know, this guy is bounded. This guy I can choose as small as possible because converges. Smaller than epsilon times this bound, no? Correct or not? I can straight away deal with this two term here in particular. Then I think the last part is you need to deal with here. But you know that BK is bounded. So immediately you jump to the last step here. You just need to make sure this is Cauchy. Is this Cauchy or not? Is AN Cauchy or not? Converge to 0 already, right? So it's Cauchy. So actually it's easier to prove. So let me show you the result here. You see? You straight away deal with this summation by parts. Okay? And then you can straight away bring in your triangle inequality. And then Bn is bounded. All the Bn bound by some m. An plus 1, An converge to 0. Converge to 0 means what? This is less than or epsilon. So you just pick epsilon over 3m. Why 3 again? You should imagine I have epsilon over 3 times, I will add them up. So where's the third epsilon coming up? Is the last guy here. An plus 1 minus An. So if you can use Cauchiness here, then you will produce 3 epsilon over 3. And then that actually it's easier proof. Easier proof. Okay, so maybe you want to ask a question. So you want to ask a question. So quickly discuss this question here. So let me quickly conclude what is Abel, what is Dirichlet. So Abel says that says what? Says that this partial sums here converges. Dirichlet says what? This partial sums here bounded. Okay. Abel says about An is what? An monotone, bounded. Dirichlet says what? An monotone, converge to 0. But both will give you that the sum of AK, BK converges. Correct? No? Okay. Okay, sorry. Yeah. Let me move. Don't move it. Okay, let me move. So, see, compare Abel's and Dirichlet. Do you think that one will imply the other or not? Very similar, no? Correct? No? Does one imply the other? Surely convergence implies bounded. Okay? But monotone implies monotone, okay, equivalent. Does bounded implies converge to 0? Maybe not. Right? Maybe bounded doesn't diverge. Okay? But won't be diverging because it's monotone must converge. But maybe not converge to 0 How about the other direction? Monotone, good. An monotone. An converge to 0. Does it imply An bounded or not? Okay. Yes. But bounded partial sum doesn't imply convergence of partial sum. When converge, if it is monotone. So it doesn't imply each other actually. Okay, so tomorrow we will discuss about one example when we can use Abel test, when we can use one test but not the other. Okay, tomorrow we'll see one example, two examples maybe. Okay, yeah, so they don't imply each other, but the proof is very similar. Okay, although they don't imply each other. We'll see example. Okay. So see you tomorrow.